Hello guys, I hope you are doing well and I hope everything is alright with you. And I hope the semester is going very well with you. Okay, so in this video we'll be discussing Chapter 18. Chapter 18 is solely about thermodynamics, which is a different field than, say, waves or electricity and magnetism. The fields that we discussed in the last couple of weeks, and the field that we'll be discussing when we finish thermodynamics, which is electricity and magnetism. So the next three chapters, which is chapter 18, 19, and 20, will be dedicated to only thermodynamics. So in the first thermodynamics chapter, which is this chapter, we'll be discussing the basics of thermodynamics. So everything we're going to talk about in this video and in this chapter is pretty straightforward. Okay, so our first topic here is temperature. Temperature is a description of the status of the material, a description of how energetic the material is, how much thermal energy we have in a system or in a material. Okay, so this is one thing about temperature. The other thing is that temperature tells you the direction of heat flow. Like heat always flow from hot to cold bodies. So this is the two most important things that you need to know about temperature. Secondly, we're going to discuss something called the Zeroth law of thermodynamics. So this law is pretty simple. And so if you have body A, and body A is in thermal equilibrium with body C, and we have another body, let's call it body B, and body B is in thermal equilibrium with body C. So if this condition is true, and this condition is true, then a third condition must be true. The condition is body A must be in thermal equilibrium with body B. So body C is like the control sort of variable. Like if we have two things that equal to the same thing, then these two things must also be equal. So A and B must be in thermal equilibrium, and which means that they must have the same temperature. Alright, so the third thing we'll be discussing is the scales of measuring temperature. Okay, so we have three scales. The first one is Celsius, the other is Kelvin, and the last one is Fahrenheit. So these two scales are very similar in many respects, and we'll see that. Fahrenheit is also a way to, or a unit, to measure temperature. But it's a little bit different from these two, and we'll see how that goes. Alright, so the fourth thing we'll be discussing is something called thermal expansion. So in thermodynamics, we know that if we raise the temperature of a body, like say body A, and the body will get more energetic. So its area will increase as well. So its dimensions, its length and height and width and whatnot. If we increase its temperature, all of these dimensions will increase. And vice versa, like if you reverse the process, the dimensions will decrease. Alright, so the next thing is heat absorption. So heat is basically energy. Like we have mathematical equations that governs the way bodies absorb or release heat. So we'll go into details later. So next, we're going to discuss something called pressure versus volume diagrams. So we will have we'll have graphs like this one. So this is volume in the x-axis, and this is pressure. And say that when we increase volume, pressure increases. So these diagrams basically explain some sort of systems. Say we have like a container like this, and we have gas molecules here. So the volume of the gas molecule is described in the x-axis, and the pressure of the system, or the pressure of these molecules, is described in the y-axis. So if you kind of push into this, and you will increase pressure. So pressure goes up if we do this. The volume goes down. And so we'll study what happens to the system thermodynamically. So this graph tells you if you take the area under this graph, it tells you how much work the system does. And we will go into this when the time comes. All right, so the second to last topic here is a very important section, which is the first law of thermodynamics. So the first law of thermodynamics is coming straight out of the conservation of energy law. And it's heavily related to the PV diagrams, and we will see that once we get there. Okay, lastly, we'll study heat transfer mechanisms. Heat transfer mechanisms, we have three ways of transferring heat from an object to another object. And in this chapter, we'll be kind of focusing on the first way, which is conduction. But we will also study the second two ways. And that's about it. That's all the points we'll use. All right, guys, so now we'll be discussing section 1 of chapter 18. So first, what is temperature? So temperature tells you how energetic the system is, or how much thermal energy we have in a system. Okay, so the higher the number of the units, so here we used degrees Celsius. The higher the number, the more energetic the system is, or the hotter the system is. So if you have a body A at 100 degrees Celsius, and we have a body B at 0 degrees Celsius, body A has much more thermal energy than body B. So temperature is an indication or a description of how much energy we have in an object. Okay, so a closely related topic to temperature is thermal equilibrium. So two bodies are said to be in thermal equilibrium if they have the same temperature or the same thermal energy. Okay, so if we have body A, as shown here, which is a hot body at 100 degrees Celsius, and we have body B at 0 degrees Celsius. So temperature tells you the direction of heat flow. So heat flows from the 100 degrees Celsius body to the lower temperature body, which is 0 degrees Celsius. So heat will be flowing, heat is energy, so a thermal energy will be flowing from A to B until the two bodies reach the state of thermal equilibrium. So we call body A and B the system. So the system will reach a temperature, which is represented by the unit degrees Celsius, that is less than 100 and more than 0. And the temperature will be common between the two bodies. So A and B will have the same temperature, and once that temperature is reached, we can say that A and B are in thermal equilibrium. Okay, so our third point here is the Zeroth law of thermodynamics. So if you have mastered the previous two ideas, it will come clear to you that if you have a body A that is in thermal equilibrium with body C, and we have body B that is in thermal equilibrium with body C as well, then that means that A and B are also in thermal equilibrium. So it's sort of very logical, very simple idea that if you understand what thermal equilibrium is and understand what temperature is, it will come kind of automatically to you that if this condition is true and this condition is true, then this condition must as well be true. And that's it. Alright guys, so our next section in this chapter will be about units of measuring temperature. So we have three common or three well-known units. The first one is Celsius, the second is Kelvin, and the last one is Fahrenheit. Okay, so the thing about Celsius and Kelvin is that the increase in Celsius by 1 unit is exactly the same as an increase in Kelvin by 1 unit as well. So the only difference between Celsius and Kelvin is that in Kelvin, the freezing point of water is 273, but in Celsius it's 0. So then if you increase 1 degree in Kelvin, it's exactly the same as increasing 1 degree in Celsius. So if you increase 100 degrees in Kelvin, then the water is going to boil. And water boils in Kelvin when the measurement is 373, and it boils in Celsius when it's 100 degrees Celsius. So the only difference between Celsius and Kelvin is the starting point. Kelvin starts at 273 and Celsius starts at 0, but other than that, they're exactly the same thing. So Kelvin is the scientific unit, and it's the unit that we will be using in all the equations. So if you're solving questions and you're asked to find the temperature, then the unit in the equation you're gonna use is Kelvin. So one important point about that is that if you're dealing with temperature difference, so say we have a temperature difference of 30 degrees Celsius. That means that imagine that we have a material at 70 degrees Celsius, and we can heat the material until it reaches 100 degrees Celsius. So the temperature difference between this point and this point will be 30 degrees Celsius. And you can plug this number into your equation. It's okay, even though the equation uses the Kelvin unit. Why? Because the difference between this point and this point is 30 degrees, okay? And we know that 1 degree, one kind of increase in Celsius is exactly the same as 1 increase in Kelvin. So when we're talking about temperature difference, the difference will be the same in degrees or Celsius, in Celsius or Kelvin. So this is also equal to 30, temperature difference in Kelvin. So if you're dealing dealing with temperature difference, then you can use either Celsius or Kelvin. So one important thing is that if we're talking about temperature difference, then the degree notation should be after the C. So if we're talking about temperature difference, then we say 30 Celsius degrees. But if we're talking about a specific temperature, like if you have, say, fire, and this fire is at a temperature of 300 degrees Celsius. So we're kind of describing the temperature of the fire. So we say degrees Celsius. But if we're talking about temperature difference, as it is the case here, we have a material at 70 degrees Celsius, and when we heat it to 100 degrees Celsius, then the temperature difference between 70 and 100 is 30 Celsius degrees, not degrees Celsius. And when we're talking about temperature difference, then we can express the difference in Celsius or Kelvin equivalently, like it doesn't make any difference. Okay, now about Fahrenheit. Fahrenheit is different than Kelvin and Celsius because one increase in Fahrenheit is equivalent to 1.8 Celsius increase. So a degree in Fahrenheit is equivalent to 1.8 degrees in Celsius, sorry. So the relationship between Fahrenheit and Celsius and Kelvin is not linear. So it makes it a little bit different. So when we're talking about temperature difference in Fahrenheit is not the same as in Celsius or in Kelvin. Okay, so and in Fahrenheit the water freezes at 32 Fahrenheit and it boils at 212 Fahrenheit. And if you want to convert between Fahrenheit and Celsius, then you plug this your value here. For example, if you have a fire at 300 degrees Celsius and you want that to be expressed in Fahrenheit, you just take this 300 and plug it here and multiply it by 9 over 5. 9 over 5 is exactly the same as 1.8. And then add 32 to it and you will get your answer in Fahrenheit. So, and if you want to convert between Kelvin and Celsius, you just subtract 273 from your Kelvin measurement. Why? Because in Kelvin we start at 273. And that's everything in section 2 in this chapter. Alright guys, so when we add heat to substances or to objects, the molecules or the particles that constitutes the object start moving away from each other. Like they have more kinetic energy and they have more thermal energy. So say we have the pen, and this pen is 5 centimeters long, so its length is 5 centimeters. Say we have a stove or a fire, a source of heat, a source of thermal energy. So, and we put it under the pen, and so the pen will be getting hotter and hotter. So what's going to happen is that the length of the pen will increase, and it will increase according to this relationship. So we have the coefficient of linear expansion multiplied by the initial length, which is 5 centimeters, and then multiplied by the difference in temperature, the final temperature minus the initial temperature. So if you multiply these three values, the coefficient of linear expansion times the original length times the difference in temperature, this is going to give you the difference in length, or how many centimeters or how many meters the length of the pen will increase. Okay, so this, if we have one-dimensional objects. If you have a two-dimensional object, so we have a square, so we have a height and we have width. And so our increase in size will be happening in both the width, so it will increase, and the height, it will increase. So we have our coefficient of surface expansion, which is expressed by y. So y is basically equal to 2 alpha. And if you multiply y by the initial area of the surface and multiply that by the temperature difference, this is going to give you how much the area has changed, either increased or decreased. So if you have a kind of heat sucking machine under this pen and the machine will be decreasing its temperature, so the molecules or the atoms in the pen will be moving close to each other, and its area will decrease. So the process of thermal expansion goes both ways. Like the expansion can be positive or negative. If we're decreasing the temperature, then the expansion is negative. So finally, if we have a three-dimensional object, so we have a cube. So in this case, we have height, width, and so if we have a three-dimensional object, so we have height, and we have width, and we have length. So our expansion will be happening in three dimensions, and the height will increase, the width will increase, and the length will increase. So in this case, we have the coefficient of volume expansion, which is beta. So beta is basically 3 alpha. And if you multiply beta by the original volume and multiply that by the difference in temperature, the final minus the initial temperature, then you'll be getting the change in volume. Like if we have like fire and the temperature increases, the final temperature is higher than the initial temperature, then our change here will be positive. So this equation will give you how much volume we have increased the cube. And vice versa. Like if we decrease the temperature, the change will be negative, and this equation will give you how much volume we decreased the cube. And that's about it. That's everything in section 3, chapter 18. Alright guys, so section 4 is about sucking heat into an object, or absorbing heat into an object, or releasing heat from an object. Okay, so we know that heat is energy, and energy is measured in joules. So if we have a very hot object, say we have a ball, a metal ball, and the ball is at 100 degrees Celsius. And we take this ball out of this board and put it here in this room. The room temperature is 25 degrees Celsius. So what's going to happen is that the ball will try to come to thermal equilibrium with the atmosphere. So heat will be flowing from the ball to the atmosphere. And the amount of heat that is going to flow from the ball is equal to the mass of the ball times C. C is a constant and it depends on the material. So C is the amount of heat or amount of energy required to raise 1 kilogram of this material 1 degree Celsius. And C unit, the unit for C is joules per kilogram. So if you multiply the mass times the constant C times the change in temperature or the difference in temperature, for example, 100 negative 25, you're going to have 75. If you multiply these three values, you're going to get the amount of energy that is going to flow outside of the ball to the atmosphere. Now, keep in mind that Q is positive when the object absorbs heat. So if you have like a 0 Celsius or degree Celsius ball, and we have an atmosphere of 25 degrees Celsius, then heat will be flowing from the atmosphere to the ball. And in this case, we're going to have a positive Q. But if heat is flowing out of the object, like in this case, so our Q, or the amount of energy, is going to be negative. Okay, so that this kind of equation applies when we have change in temperature. So what if we have like change in status? Imagine that we have ice, okay? Ice at 0 degrees Celsius. And that ice is going to be exposed to some sort of thermal energy, and then it's going to melt, and we can have some water. How can we calculate the amount of energy required to fuse the ice into water? So we have something called latent heat of fusion. So latent heat of fusion is a constant value. And if you multiply it by the mass of the ice that we have, say we have 5 kilograms of ice, then you're going to get the amount of energy that is required to sort of melt the ice. So the latent heat of fusion and the latent heat of vaporization are constant, and will be given the equation sheet. And in order to calculate the amount of energy that takes to either vaporize water, like if you have water and we want to get water vapor, you just multiply the constant value, the latent heat of vaporization, by the mass of the water. And this also goes both ways. So if you have water vapor and we want to turn it into liquid water, so we're going to use the latent heat of vaporization, the constant value, and we're going to multiply it by the mass of the water vapor. And the only difference between turning water to vapor or vapor to water is the sign. So if heat is flowing, as we just explained, if heat is flowing outside the material, then we're going to have a negative Q. But if heat is flowing to the material, so we're making the material harder, like so we're gonna have a positive Q. So like the case of vaporizing water, we're adding heat to the water, so we have a positive Q. But if you want to turn, for example, water into ice, so we're stuck in or taking the heat out of water, or taking the thermal energy out of the water, then we're gonna have a negative Q. And this is the latent heat of vaporization of water. So if you have liquid water and we know its mass, say it's 5, then we just multiply it by the latent heat of vaporization, which is this value, mass times latent heat of vaporization, and you will be getting the amount of energy that it takes to in order to vaporize water. And that's it. All right, guys, so chapter 18, section 5, in specific subsection 5, is very, very important. And the concepts of this section is going to carry with you and in the next section and the section after it. Okay, so it's about pressure versus volume diagrams, and it's about the first law of thermodynamics. So in this section, we're going to study three things. We're going to study pressure, volume, and heat. So imagine we have a system like this, and we have some sort of gas inside the system, inside the container, and imagine that we have a piston. So the piston here represents the pressure in our graph. And the volume here in the x-axis is represented by the volume of the gas inside the container. And imagine that we have some sort of heat here. And we have some sort of controller we can turn on and off. Okay, so if we decrease pressure, if we push the piston downward like this, so the volume is going to decrease. So we're going to have, okay, so if you push the piston down, the pressure on the gas will increase and the volume of the gas will decrease. And we can represent this process, the step 1 to step 2, by this graph. So first, we were here. This is the initial point. And we push the piston down, so we increase pressure. So pressure goes up. And volume goes down as we move along this line to the final state. Okay, so if you want to calculate the work done by the gas on the piston, then we're going to have to calculate the area under this curve. So imagine as you push the piston down that the gas is exerting some sort of upward force. The gas is exerting force on the piston in the upward direction, and the displacement is in the down direction. So we know that work is basically force dot displacement. And if these are in opposite direction, we're gonna have negative work. So the work in this case is going to be negative. And generally, as a general rule of thumb, if you have decreasing volume, like if you're moving from right to left, then we're going to have negative work. And work is basically the area under any pressure versus volume graph. It's the integral of P, dV. Okay, so this is an example of like how can we interpret the pressure versus volume graph. Okay, so in this graph, we know we can see through the graph that from point A to point F, the pressure is dropping. Like we're moving from a higher pressure to a lower pressure. So, which means we're going from here. So in this case, in this graph, this is the first. This is 1. This is 2. So we were like this, and we kind of lifted the piston up. So we decrease the pressure, and once we lift the piston up, we can have a bigger volume, as it can show here. So in this graph, we're moving from left to right. So our work is the area under this curve, and it's going to be positive, okay? And if you want to understand this conceptually, you can look at it this way. Like, we know that work is force dot displacement. Okay, so if we're decreasing pressure, the force exerted by the gas on the piston is an upward force. And the displacement is in the same direction, like because we're moving the piston upward, so we multiply F by X, we're going to have a positive value. So now imagine that we first go from A to F, like we kind of lift the piston up, and we increase the volume of the gas. So we have this sort of graph, and the area under the curve is the work. Then after we get to the F point, we start increasing pressure again. Like we're here, we start pushing down on the gas. So we increase the pressure and decrease the volume. So our movement will be from right to left. So the work done in this case is the area under this curve. And it's going to be negative work. So if we do this, if we go from A to F, and then from F, the original F here, to A to I, so what's the net work? If we sort of go up and down in this kind of setup, so we know that the original work is basically the sum of these two works. So let's call this 1 and let's call this 2. So positive W1, negative W2 is going to equal to the net work. And we can see that the work here, the positive work, is a little bit bigger, the value of it bigger than the negative work. So if we add these two together, you're going to have a shape. If you add this graph to this graph, you're going to have a shape like this. And this here, the area inside the two graphs, is equal to the net work. Because what we did, basically, we took this value, this area, and we subtracted it from this area. So we get this sort of shape, and this is the work done in the system. All right, sorry, this is the work done by the system. I mean by the gas on the piston. All right, so we know, is this work positive or negative? So we know that it's positive. Why? Because as we can see from the graph, that the area under the positive curve is bigger than this area. So we basically took this area, the negative work area, and we subtracted it from the positive work area. So we have some left over from the positive work. So this must be positive. Okay, so very close to the setup and this pressure versus volume graph is the first law of thermodynamics. So we have defined some value called change in internal energy. So this is change in the internal energy of the system, and we found that change in internal energy is a constant value. Like if you have a setup like this, change in internal energy is always equal to Q minus W. It's constant if we're moving from point A to point F. Like if we move in this path, or we move in this path, the change in internal energy will be the same thing. Like if we have a point, say I, and we have a point F, if we move from I to F, the change in internal energy is constant. Like if we go like this, or we go like this, or we go like this, this is going to always be constant. So the only thing that changes if we change the path is the work done by the gas on the piston and the supply of heat. So as far as the heat goes, all right, so imagine that we have a graph like this. So our pressure here, or the piston, is unchanged, okay? So what we are doing is basically turning on the heat here, on here, and increasing the temperature of the gas. As we increase the temperature of the gas will expand. So our volume is going to be increasing. So as the volume expands because of the heat, the gas will exert a force on the piston in the upward direction, and the piston will be displaced upward. So if we multiply our force by the displacement, we're going to have the work, and it's going to be a positive work. It's the area under the curve. So our three kind of variables that can change is pressure, volume, and heat. So according to the law of the first law of thermodynamics, we're basically adding heat to the system. As we said, we increase the heat by turning on the fire, and we've done positive work. So the difference between the heat added, to the work done by the gas is always going to be equal to the change in the internal energy of the system. This here is a mathematical statement of the first law of thermodynamics, but if you want to state it sort of verbally, we say that the change in internal energy of this system tends to increase if we add heat to the system. So if we add heat to the system, the change in internal energy will increase. But if the system does work on the piston, then the change in internal energy will decrease. That's why we have a negative sign here. Okay, so if the gas does work in the piston, then the change in internal energy will decrease. Okay, so this is the statement of the first law of thermodynamics, and this was found experimentally. It was experimentally found that if we move from point A to point F through any path, that this value does not change. And now we're going to look into some special cases of the first law of thermodynamics. Okay, so now we're gonna be looking into some special cases of the first law of thermodynamics. There are 4 special cases, and they are pretty simple. And if you understand them, they will help you to understand or to reinforce your understanding of the first law of thermodynamics. So our first special case is called adiabatic process. So if you want to translate adiabatic in English, so it means no heat or constant temperature. So like its name, adiabatic, in an adiabatic process, our first law of thermodynamics is basically change in internal energy is equal to the heat added to the system minus the work done by the system. So if we add no heat, if this term is out, so we have a system here and we have no heat at all. The system is completely isolated from its environment, and there is no source of heat that can affect the system. So in this case, if the gas does positive work, which means it displaces the piston upward and by a force that is going upward, then our internal energy of the system will decrease. But if the gas does negative work, which means if we push the piston downward, so the displacement is downward, and it becomes something like this, and the gas is compressed like that. So we know that the gas will be exerting force on the piston, and we're going to have negative work. So if we have negative work, then our internal energy will be something like this, which eventually will be like this, will be positive, okay? So if we do that, if the system does negative work and there is no heat involved in the process, then our internal energy will increase, okay? So this is the first special case. It's called an adiabatic process, and adiabatic means no heat transfer or no temperature change. Okay, so our second case is a case when we hold this piston in a constant place. Say at y is equal to 5. If this is the y-axis, we hold the piston at y is equal to 5. We place our hand like this and we hold it constant in a constant y position. And then we add heat to the system. So we know when we heat the gas up, the gas will try to expand and try to push on the piston, but in this case the gas cannot push because we're holding this stationary. So the second special case, all it says is that when this is the case, when we hold the piston constant and we add heat to the system, then the internal energy of the system will increase. That's the second special case. So our second to last special case is a case in which we start from point A or I to point F, and then we go back to point I. So we know that the change in internal energy of the system will be 0. So our cyclic sort of special case says that Q must be equal to the work done, or the heat added to the system must be equal to the work done by the gas on the piston. Our last case is called free expansion, and it's a case. Imagine that we have so much gas in here, and it's condensed, so it's pressured out. And suddenly, we remove this partition here. So the gas will be rushing towards this here area. So this is called free expansion. So in a free expansion, it's an adiabatic process as well, because there's no heat involved, or there's no heat transferred to the system or out of the system. So in any process that heat is not involved, we call it adiabatic. So our last case is also called adiabatic, and it's a free expansion sort of case. So we know that in this case, heat is 0. Okay, so our equation becomes something like this. So heat is 0 minus the work. So there is no piston here. So this is the piston, but we have no piston. Like the gas is spreading out freely. Like the gas is not doing any work or anything. Like the gas is not doing work on anything, and nothing is doing work on the gas. So this is also 0. So which means that the change in internal energy of the system is 0. So this is a pretty simple case. It just means that there is no heat and there is no work. So the internal energy, or the change in internal energy, is 0. And these are the 4 special cases that are included in our syllabus or in our course. And if you understand them, it will help you understand the first law of thermodynamics further. And that's it. Okay, so our last section of this chapter is about heat transfer. Heat transfer is basically when we have a hot object and a cold object, and we have some sort of medium or some sort of rod here connecting the two objects. So what's going to happen is that temperature will flow through the rod from the hot object to the cold object. And the energy or the temperature will be flowing at a rate that is equal to something called K, or the thermal conductivity of the material between the two bodies. And K will be multiplied by the cross-sectional area of the rod, cross-sectional area. And that is going to be multiplied by the difference in temperature. For example, if we have 90 degrees Celsius and we have 0 degrees Celsius, then the difference between the two temperatures will be 90. And that is divided by the length of the rod, or the conducting medium. So if you kind of plug this into your calculator, you'll be getting the conduction rate. The conduction rate is the power, or the amount of energy transferred per unit time. So what if we have two materials between the hot and cold bodies? So one thing you need to know is that the conduction rate, or the speed of transfer of energy between the hot and cold body, is constant. So this value here will be constant. Either we have one slab or two slabs. And if you want to calculate the conduction rate, all you need to do is you plug your numbers into this equation. So if you have composite slab, then you change this equation to this equation, and this equation is basically derived from the first one, but for some algebra and whatnot. So this is for our first sort of heat transfer mechanism. Okay, so our second mechanism of heat transfer is called convection. And convection happens when we have a fluid, say air or water, and we have some sort of heaters. Okay, so this is a fire or a source of heat. So, and imagine that this container is filled with water. So the water that is in the bottom here will be hot, will be hotter than the water at the top. Okay, so because the temperature increased in the water in the bottom, the molecules or the atoms of the water will going away from each other. So if we take like a microscope right here and we look into here, we'll see that the molecules are actually far away from each other, like this. But if we look here, we'll see that the molecules are very close to one another. And the molecules down here are far from one another because of the energy, because of the kinetic energy that is transferred from the fire to the molecules. So because of this difference in densities, density down is much smaller than density up. The molecules in the bottom of the container will rise, okay? And this high density molecules will go down here. Okay, so once the higher density molecules come into contact with water, they will be getting hotter and thus less dense, and they will go up again. And the denser molecules will go down. So it's like a cycle that's keep going on and on until the heat is transferred through the whole liquid or gas or whatnot. Okay, so our last technique of heat transfer is radiation. So the amount of energy that a body emits, or actually the rate at which a body emits energy, is equal to Boltzmann constant, which is this. It's a value that's given, and it might be given in your equation sheet. This value must be multiplied by the emissivity of the object, and it's some sort of measurement of how good of a radiator the object is. And it's usually a value from 0 to 1, 1 being expressing or explaining an object that is very good at radiating, and 0 is an object that is very bad at radiating. And that is going to be multiplied by the surface area of the object. So imagine that you have a mirror, a circular mirror. So pi r squared is the surface area of our radiator, and multiplied by the temperature in Kelvin of the mirror or of our emitter or radiator. So the temperature must be in Kelvin, okay? So this is how we calculate the rate or the power or the energy transferred per unit time when our heat transfer mechanism is radiation. So one point, and one thing that I need to point out is that an object in any atmosphere or in any environment both emits and receives energy from its environment. So in order to calculate the net power, this here, the temperature, must be expressed in this way. So T being the temperature of the environment of the object, and T, the first T here is the environment, the temperature of environment, and the second T is the temperature of the object. So this is the equation that you should use in order to kind of calculate the rate of or the net rate at which the object transfers heat. You need to put into account that the object both emits and receives heat or radiation. And that's it. That's all about this sort of technique. And this technique is not heavily tested. Like, according to Professor Kunwar, there has been only one question in last year, I think, and no questions in any year other than last year. So that's it. That is our first chapter about thermodynamics, which is chapter 18. I hope you guys enjoyed the video, and I hope you got some benefit from it. And thanks for watching.